Thank you, and in particular I'd like to thank the organisers for this wonderful conference and giving me and all of us the chance to talk and to listen and to be here. I'm going to talk in some work in progress with Anne-Marie Bowman, Mike Hill and Magdalena Kajura. So, I claim that homotopy theorists want to study topological homotopical information by replacing it by algebra, because algebra is easier to work with or easier to compute with. So then, if we're going to do equivariant homotopy theory, we should do equivariant algebra. So, in case you haven't seen this before, let's just get a little table: algebra, equivariant algebra. Okay. So, we want to do something additive. What would we study in algebra? We study abelian groups. What's the equivalent in equivariant algebra? It's going to be Mackey functors. If we wanted to add a multiplication, well, we'd get rings here. And then in equivariant algebra, we would get ring functors, or we would get Tambara functors, depending on quite what multiplication we want and how we set up the monoidal structures and so on. And then we wanted to add something with an action. Instead of a multiplication, here we'd get modules. And, well, I mean, here we can talk about modules over green functors, and we can talk about modules over Tambara functors. And then, to make things even more interesting, we also have incomplete versions of these. Magdalena talked about some incomplete Mackey functors, and Scott's going to talk to us about incomplete and possibly bi-incomplete Tambara functors. So we'll see that, so I don't have to define it. And I want to make the statement that we should popularise the term equivariant algebra. Like, it's a useful term, it's a good thing to have a name for something, right? And we should popularise it as distinct or building on algebra. Because the thing that the algebraists want to do and the representation theorists want to do often has something of a different flavour from what we're trying to do. And we'll see a bit of that today, and I'm going to start with a question from equivariant algebra, and it's going to take us a long time to get it down to something that the algebraists know. I further claim it's more interesting in that we've already got a choice here of the different structures, and the incomplete versions behave very differently. I mean, the analogy is strong in that one can define ideals of these things. As Scott, you're going to define ideals of Tambara functors, right?
I will recall the definition.
Excellent. Good. Here's another example as to how equivariant algebra is even more interesting than ordinary algebra. Okay, so in algebra, a free R algebra is flat as an R module. Okay. In equivariant algebra, free incomplete Tambara functors are almost never flat. And this is a fairly recent result of Hill, Murray, and Quigley. The point is that new phenomena occurs in equivariant algebra, And so we might like to sort of think, how can we remember this result? Well, I don't know if Hill and Erlang quickly have a name for this, but I think I do have a good name. We should call it the butterfly theorem. Because of a quote from Bjorn Dundas which says, butterflies are free, but they are not flat. It's kind of rude to name someone else's theorem in your talk, but, you know. Okay, good. So, you're all sold on equivariant homotopy theory. And equivariant algebra is a way to study it. Aim. Understand the homological complexity of categories from equivariant algebra. We're going to use it to calculate stuff in. We're going to use the tools of homological algebra. So we want to know how difficult it is to actually go and do these things, how much time it's going to take, and so on. So, let's talk about global dimension. Maybe it's been a while since one has thought about the term. Well, it's pretty early in the talk, so I think I can afford to tell people this level of information. Okay, so, definition. Let's have A be an abelian category with enough injectives and enough projectives. Okay. The global dimension of A is, okay, so the maximum of the injective dimension of objects of A. It's going to be a long definition, so give me a moment to finish. Maximum of the injective dimension of the objects of A. What's the injective dimension of an object? It is the length of the shortest injective resolution. So you pick an object, you find the shortest injective resolution, that's the dimension of the object. Now we look along all of those values, and if that's bounded, we call that the injective dimension. Okay. The maximum of the projective dimension of objects of A. And I'm saying that both of these numbers are the same. How do we see they're the same? Well, it's the same thing as the largest n such that x in A of n from A to B is non-zero, for AB in A. And then, just in case you were anxious, how do I know these things are bounded above? Let's say for infinity, if these values are not bounded. Okay. Seems like a reasonable definition, right? Possibly a bit hard to calculate, but essentially, you know, it gets the right flavour. How bad is the homological global dimension of A is a measure of how many X groups we have to worry about. So let's do Let's do some examples. Maybe people remember a bunch off the top of their head. Okay. But it does require a bit of effort to calculate it in some cases. So let's have a category. Let's have global dimension and a space for notes. All right, so we start with the groups. And as we remember, this has global dimension 1. Why? Because you can write something in terms of generators plus relations, i.e. a free resolution of length 1, and then you can calculate that using that resolution, you do actually get non-zero x1 groups. Okay? So easy enough. What if we looked at Q modules? Well, we get 0, because the category is semi-simple. Okay. Well, if we wanted more interesting options, so we could look at polynomials over Q in n generators. This has global dimension n, and Wikipedia tells me this is Hilbert's syzygy theorem. Okay. What about something just a little bit equivariant? Well, we could look at group rings for G non-trivial. And then we get the extreme case, we get infinite global dimension. How do we see this? Well, we could just look at ZC2, and we've got a map here, 1 minus sigma. Sigma is the non-trivial element of C2, ZC2, 1 plus sigma, ZC2, 1 minus sigma, and we keep going. And as many of us remember, this is a resolution of the integers as a module over ZC2. And this resolution is infinite, and when you can calculate the extra groups and see that they're unbounded. And, well, if it's infinity for C2, you can believe it's going to be infinity for CP, and then you can extend up to other groups and so on and so forth. On the other hand...
G being finite here?
Oh, yeah, G finite. Right? If we took rationals, we get 0. That's Mackey's theorem. So, sometimes it's quite straightforward, sometimes it requires a bit of work. In general, it's a reasonably non-trivial thing to try and work out.
How is this related to the categorical level of the derived category? Is it the same or?
Categorical level?
Like how truncated the Hom objects are. Because those are some of the Hom objects, but not all of them, right?
I mean, I would naively say that in the derived category, the derived Homs are the X groups, and so the truncation is the global dimension. I mean, I'm seeing someone nod. Thank you.
Okay. Yeah, I was just wondering because I guess maybe not everything is concentrated as one thing.
So let's go on and do some of this for equivariant. Keep pulling them down because I'm used to not having enough height to put them out of the way. Okay, so let's do finite. Let's look at compact Lie. Let's look at the pro-finite cases, at least a couple of them. Let's do some global dimensions over here to show it's at least as interesting as the other and possibly a bit harder. Okay. So, the category, we're going to have the global dimension and notes. Okay, so if we take G finite, we could look at Mackey functors for G. We have to say G non-trivial, otherwise we of course just back in abelian groups. And the global dimension here is infinity. And it's the same answer as for ZG, because any ZG module gives you a Mackey functor, and then you can go and calculate. There's no extra space in Mackey functors to get rid of these infinitely long resolutions. Or we can look at rational Mackey functors, and we get 0. And this very much isn't Mackey's theorem. This is a theorem of Greenlees and May, and also at the same time a theorem of Thevenaz and Webb. Forgive me for not putting the, I'm going to put an accent there and hope that's correct. This requires real effort to actually prove, right? So we get the extreme cases when G's finite, right? What about if we try and look at something in the compact Lie case? Okay. So let's say I want to look at SO2 or S1, whatever you want to call it. I don't actually want to look at Mackey functors for SO2, because that's not where we're going to actually do our calculations in equivariant algebra. Instead, we want to look at this algebraic model of John Greenlees, who's going to tell us all about this monoidally on Friday. So therefore I don't have to define it, you just have to wait till Friday. But I mean, it's a nice category, it's where you calculate things. If you're trying to do any kind of calculation in S1 spectral rationally, you push down to this category, you use the Adams spectral sequence, and you get your answers. What is its global dimension? 1. Except I'm lying, because the global dimension isn't defined, because this category doesn't actually have enough projectives. So really this should be the injective dimension. But the spirit of the result is the same, right? You're trying to do homological algebra. How bad do you get? You get exactly dimension 1. There's another model. Sorry?
What exactly is this category, A, SO2? What kind of representation is there?
I mean, you want me to define the category?
Or you can just say in words, yeah, sure.
Okay, good. Right, so you take QC, where C is degree minus 2. You take the product of QC's over the finite subgroups of SO2. That's now called OF. Okay. Now you take the Euler classes, which is this of SO2, and you invert that, you call that TF. ASO2 is the data of an OF module to TF tensor V, where V is a graded Q vector space, such that when you invert the Euler classes, that map becomes an isomorphism. Okay. If we look at the torsion model, this is again a model for rational SO2 spectra, in that I can put a model structure on objects with a differential in this, and I can get a Coulomb equivalence to rational SO2 spectra. Or if you like, you can say that the derived category of this category is equivalent to the homotopy category of SO2 spectra. This has got injective dimension 2. And so really, I include this here as a caution. It's not set in stone. Like, I can give you a category, I can find an algebraic model for it, it's got injective dimension 1, I can find another that's got injective dimension 2. So this injective dimension isn't really preserved by Coulomb equivalences or derived equivalences. One needs something a bit more careful. So a bit more subtle in order to capture that. On the other hand, it gives us the freedom to choose, and from my perspective, that's why this category is the better option. And John's welcome to have different opinions on this. Okay. One can extend this to R torus, i.e. R copies an R-fold product of SO2. This has dimension R. And then one can go further. I use G. Now, this should be the rank of G. Again, it's injective dimension. And this is remains a conjecture.
Known for many groups.
Known for many groups. Exactly, it's known for this group. Okay, good. I want to do one more case, in that I want to do for finite groups, and now we're back to Mackey functors, right? As this is a good algebraic model for the category. And now the answer is one takes the rank in the sense of Cantor-Bendixson of a space of closed subgroups of G and subtracts 1. Okay, so that requires an actual bit of explanation. So, I give you your profinite group G, so G is compact, Hausdorff, totally disconnected. It's the inverse limit of a filtered system of finite groups. You've got a topological group. You can look at the set of closed subgroups and you can give that a topology using the Hausdorff metric. So you have a space of closed subgroups. That's a profinite space. And you can perform this operation where you say, I'm going to take this space and I throw away all of the isolated points. You get a new space. You can throw away all of the isolated points of that and you get another new space. You keep going. You perform this operation of throwing away the isolated points. If after exactly n steps you get the empty set, we say that that space has Cantor-Bendixson rank n. So if I give you G, if that's got rank n, the global dimension of that category of Mackey functors is n minus 1. There's some subtleties I won't go into, and you can get infinite dimension and all kinds of bits and pieces. It doesn't have to end in the empty set, but we're not worried about that. For the nice cases, it ends after finitely many stages of throwing away the isolated points. Good. And I put this here because it kind of shows that whatever the answer is, it's related to something deeply topological. There's no easy way, as far as I can tell, and the people who've studied this even more, to calculate the Cantor-Bendixson rank from the group G. Like, that's not an immediately answerable thing. And so you've started with some homotopy theory, you've moved over to some algebra, and now you want to understand something about an algebraic world, and you're back to some topological invariant. That's the message to take away.
What's the value for P-adix?
1. Or rather, P-adix has got rank 2, so dimension 1. If I take ZP cross ZQ, I get one more, right? If you take ZP cross ZP, you get the Pelchinky space for the space of subgroups, and that's got infinite dimension. If you take ZP cross ZP cross ZP, you still get the Pelchinky space. Okay.
Has anybody thought about things like another stabilizer group?
I mean, yes. Do we have any answers? No. Okay. Let's move on. Let's look at incomplete Mackey functors. So back to finite groups, because incomplete Mackey functors are complicated enough. You saw the definition in Magdalena's talk on Monday. I'm not actually going to define them, but I will define the terms that I use. And so our aim is pick a group G, look at some category of incomplete Mackey functors, calculate the global dimension. Okay? So I want to draw just a little diagram, rational Mackey functors. We then have O. Everything's going to be rational because otherwise it's just too difficult and everything's probably just going to be infinity, again, as we saw in the earlier integral cases. So I can forget from rational Mackey functor to G, and I can forget down to an O Mackey functor, because what is an O Mackey functor? It's a Mackey functor, but it only has some, I'm going to say some inductions, okay? This has all inductions, this only has some inductions. Functor is not essentially surjective, as Magdalena said, so there are more things here, so there's new things we have to worry about. Or I could forget all the way down to rational coefficient systems for G, otherwise known as functors from the unstable orbit category into Q modules. So you've got no inductions. You've only got restrictions and conjugation maps. Okay? And one can forget structure here. Okay. We know that the global dimension here is, this has global dimension 0. Global dimension here, we don't know. And the global dimension here, we don't know. We do know something. I mean, upper bound for the global dimensions is length of longest chain of inclusions subgroups. So you look at the subgroup lattice, you look at the longest chain, that's going to give you an upper bound, because when you try to calculate something like the projective or injective dimension, you're essentially doing induction along the group poset, either downwards or upwards according to whether it's projective or injective. So an upper bound is easy to find. But we'd like to sort of try and work out what's going on here and here, and so we kind of want a lower bound. There's another point to make, which is if O is disk-like, this splits as a product of coefficient systems. So the middle term is the most complicated, so therefore we should start with the easier term and look at coefficient systems. But in disk-like cases, that actually is the answer, because this just splits into the coefficient systems anyway. Okay? So, we've got a question, right, which is find the lower bound for the global dimension of rational G coefficient systems. Okay. That's a reasonable task we set to ourselves. We'll go do that. We'll just go calculate it, and we'll find an answer nice and easy. So we tried and get an answer immediately, and we thought, okay, well, all right. Maybe we should go look at an even simpler case, right? Just keep making the problem simpler and simpler until you can actually get some numbers. Okay. So, let's get rid of the group actions, because they definitely make things more complicated, possibly not really any more complicated in terms of global dimension, but let's see if we can get rid of the group actions. Okay. So, we have a lemma. Let's define sub G mod G to be poset of subgroups of G up to conjugacy. Okay, easy enough. Now there's no group actions anywhere. And let's define rational presheaves at G just to be functors out of this poset sub G mod G op into Q modules. This is a subcategory of co-FG. I'll give you something on the rational. If you've got one of these presheaves, you can turn it into a coefficient system by just sort of expanding it out, right? I just put Q everywhere. I put in whatever G actions I have for muting the copies. It's easy enough to sort it out. Okay. And we get the global dimension of this presheaf category be less than or equal to the global dimension of these coefficient systems. Good. So now I've got a really simple category to work with. I'm just taking a poset, I'm putting a Q module at each vertex of the poset, and a map every time I have an arrow in the poset.
G is finite.
G is finite. I find global dimension a bit difficult to work with when I'm looking at adjunctions. I mean, just because you've got an inclusion of a subcategory doesn't mean that you actually have a relation like this. I needed to actually do something a bit more. I'll put that lemma up just because if anyone knows more about how inclusions of subcategories and global dimension works, please come talk to me afterwards. I'd love to learn some more. So if I have C contained in D, subcategory, both abelian categories, both enough injectives plus projectives, and let's call the inclusion iota, and iota assume iota as left and right adjoints, and they are isomorphic. So I've seen this be called a quintessential localization. It's quite a strong set of assumptions, but it's what we get in this case. Then we get the global dimension of C is less than or equal to the global dimension of D. That's how we get this result, right? So I have the inclusion, I check it has both adjoints, I check the two adjoints agree, which rationally is trivial, and then I get a relation on the global dimension. Just having a subcategory isn't enough. Just having a subcategory both with an adjoint isn't enough. I mean, maybe if you just say, oh, well, the inclusion has an adjoint and the inclusion preserves projective or injective resolutions, then that's going to be enough, but that's a bit awkward, and the only way I ever managed to prove that was by showing that both adjoints exist and they agree.
Was it at all necessary to refer to Q?
Sorry?
Was it necessary to work over Q?
For the top one?
I think you get the assumption anyway.
Yeah, but I think if I want them to be the same, I want them to agree, because I'm probably going to be taking fixed points and orbits.
That's what the left and right are.
In my head, yes.
Okay,
All right. So, let's do some examples. Okay. Group and the global dimension of rational pre-sheaves G. So, CP, dimension 1. CPQ, dimension 2. CPQR, dimension 3. Pattern's easy, right? We know what the answer is in general. Except, if I put CPN here, I still get dimension 1. Lots of things have got dimension 2. In fact, so many things that every time we try to calculate one, we draw out a post set and we start calculating. The answer came out as 2 again. So, C12, cyclic group of 24, C2 cross C2, they all give us dimension 2. C2 cross C6, that has dimension 3. If anyone here can see the pattern, please come and tell me afterwards. I claim the pattern is complicated, and we're going to see this when we actually get to possibly the only theorem in the actual result. Oh no, we've got 2, because we have the butterfly theorem. Okay, so what we've reduced our question down to is, what is the global dimension of rational pre-sheaves, the P, a post set? Okay. Most often that post set is going to be sub G mod G. It doesn't have to be, because in the original splitting result, I mean, you can, well, for Mackey functors, you can get other post sets which aren't just post sets of subgroups. So we just move to the post set thing in general because it fits a little bit better. Now, I was slightly rude to the algebraists at the start, saying they don't tend to do the things that we want to do. But sometimes they do. This is an example of such. Hands up, who's heard of incidence algebras? Yay. Okay, good. So I'm going to describe some work from Guza and Zachariah from the year 1990. Hands up who was doing maths in the year 1990.
What does doing that mean?
I'll leave that to the person to define. Right? Okay. So, an instance algebra is a type of quiver with relation. And I'm going to give you a definition that's a bit more direct than the quiver with relation term, because I really don't want to have to define quivers, they annoy me. Okay. So, we're going to have our post set P. It's going to be finite. Can do an infinite version, but I don't want to, we don't need to. Okay. QP is vector space with basis big X, where X is a vertex. Okay. So, product of copies of Q, one for each vertex. Okay. The rational incidence algebra. You can use a field, you can use a ring, but we're just going to stick with the rationals for today. IA of P is the subalgebra of endomorphisms QP to itself of those F such that if I take F of Bx, I write this as the sum of alpha y, so these can be my coefficients, by, these are my other basis elements, but we require that the y's be less than or equal to x. There's other definitions, so if you've seen a different definition, you're like, that's not how I would define it, that's fine, there's plenty of equivalent versions. Essentially, we're saying a sort of a special subset of upper triangular matrices. Okay? Right. We have the definition of incidence algebras. How do they relate to this free sheaf category? Well, it relates in the best way possible. The module over this incidence algebra is exactly the same thing as a rational free sheaf on this poset. So in some ways it's just a language issue, right? We would want, many of us would like to say free sheaves because we understand that, functors, categories, and so on and so forth. But the algebra is, at least back in the 90s, I believe, weren't so comfortable with those phrasings, they'd rather say things in terms of algebras. And now in some ways the answer's clear. You know how to find x to an algebra, it's nice and straightforward, we know how to do that kind of thing, right? So I've translated it from something a little bit sort of difficult, where maybe the answer's a bit hard to see, to let's go find x to an algebra. You might want to do this for some of the other cases, but if anyone knows how to do that in the profinite case and get this Canton-Dixon rank out, please come talk to me. Let's do an example just to illustrate this, okay? Let's have P do the poset y to x, okay? By is going to be 1, 0. Bx is 0, 1. The incidence algebra is just 2 by 2 upper triangular matrices. And if I define Ey to be 1, 0, 0, an idempotent that projects just onto the y coordinate, Ex as 0, 0, 0, 1, and Fyx as 0, 1, 0, 0. This is a basis. And M in IAP module is exactly the data of a map Fyx from Exm to Eym. Okay? And we've got the contravariance already built in to this definition. Okay, good. It's a finite dimensional algebra, so in order to calculate x groups, we only have to look at x between simple modules. What are the simple modules? Are just Q at some vertex. Okay? In the free sheaf language, that's just a skyscraper. You put Q in a particular place, you put zeros everywhere else, that's going to give you a simple module. So all we've got to do is calculate x between these things. Great. And Aguza and Zachariah did this. They came up with an answer. That gives me my lower bound. So now we know something about the global dimension of these Mackey functor, incomplete Mackey functors and the pieces of the splitter. Okay. So, theorem by Aguza and Zachariah from the 90s. Okay. The finite poset x, y vertices. Okay. So, if y is less than x, let's define the interval from x to y to be a set of vertices z such that z is strictly between x and y. Okay? So just the subposet of those things between x and y, the interval, for those of you who know the language. Okay. X star in this incidence algebra from Sx to Sy. I needed an assumption. We're going to assume that this is non-empty. We'll do with the other cases in a second. Is the reduced cohomology shifted by 2 of the geometric realization of this interval with rational coefficients. Geometric realization of the nerve.
With Sx and Sy doing a simple module at x.
Yes, thank you. Okay, so you've got an answer, and I claim that this explains why you couldn't see a pattern. It requires, you know, an actual bit of effort and thought. I claim this is not entirely sort of trivial to work out, even if I drew the poset for you. So this is the main part of the theorem. If the poset is empty, then you just get an x1, which is a q. If x equals y, you only get x in degree 0, where it's q. And if y is not less than or equal to x, then you get no x groups at all. Okay? So we get this. We get if y is directly below x and nothing in between, we get 1. And all the other cases are uninteresting. Okay. Let's just do an example, just in case I was looking at the theorem doesn't know exactly how this works out. Let's take CPQ. We get this poset. Okay. And then we can x2 from the simple at CPQ to the simple at the trivial group as Q, Y. Well, what's the interval? It's this. 2 vertices, no maps. It realizes to an S0 when you're taking reduced cohomology. Good. On the other hand, if I took CPQR, right, we get the cube. And then when you take the interval from CPQR to the trivial group E, so X from the simple at CPQR to the simple at E, and I want X3. This is going to give you Q, Y, because I have this, which realizes to give you an SY. Okay. So again, we get topology coming into our algebra that we're using to try to understand something about our homotopy theory. And one can go away and rather happily and merrily calculate these things. In most cases, one's just going to end up with the homotopy type of a wedge of spheres. It's actually a conjecture from Shirayasan from 2003, that if I give you a finite group and you take the interval from the top group, you take any interval in it, in this form, then the realization is the homotopy group or wedge of spheres. And as far as I can tell, that conjecture is still open. It's known for solvable groups, but in the general case, it's still open. Okay. So there's a theorem that Anik and Green, and this here is from 87, so even further back in time. If P is a finite planar poset, global dimension of this instance algebra, at least in the rational case, is at most 2. This was kind of the problem. Every time we drew something, we didn't want to get something too complicated or difficult, so we drew a finite planar poset, and you get 1, 2, or 0. So it was satisfying to see this result as to why we kept getting the answer 2 all the time. Got time for one more. So there's a thing called the Dushnik-Miller dimension, also known as the order dimension of a finite poset P. Anyone here know Dushnik-Miller dimension? No takers, good. So it is the following. Is the smallest t, and as ever, if it doesn't exist, one just finds it to be infinity, smallest t such that there is a set R. We can define a bunch of relations, less than 1, less than 2, up to less than t, of total orders. So I want to see that there are t total orders, each of which on P, each of which extends the partial order whose intersection is P. So I'm going to write P as the intersection of a bunch of total orders. What's the smallest number I can do so? What this is in my head is it's very much, I want to include P into Rn such that every edge of P is parallel to one of the axes, right? That's like the geometric picture that underlies this. Include P into Rn so that all of the arrows are in line with one of the axes. And there is a theorem. If G is a cyclic group, global dimension of the poset of subgroups of G, or rather the global dimension of the incidence algebra of the poset of subgroups of G, is the Dushnik-Miller dimension of sub G. So that's why you're getting this pattern CP is 1, CPQ is 2, CPQR is 3. So it was quite fun to see these results. Oh, question?
Is it sub G or sub G mod the conjugation? Oh, right. Thank you.
And so we've got a bunch of questions to go on with this. I mean, our posets, where we start off, generally have some kind of group action. So is there a notion of equivariant incident algebra? Where there is, by Nicholas Proudfoot, and we're going to see if we can understand that enough to get us better answers in the general case. And maybe I'll just finish with one conjecture. So G, a finite group, a global dimension of incidence algebras of sub G, and I'm going to say sub G mod G in this case is the largest n such that there exists H, a subgroup of G, with x to n from the simple at H to the simple at the Frattini subgroup of H is non-zero, right? The global dimension is realised by looking at the Frattini subgroups, and we run this over not just G, but we have to run this over all the subgroups. Where the Frattini subgroup is the intersection of all maximal proper subgroups. We think this should be true, and in all the examples we can draw, it works out, but we're a little bit anxious about drawing all the examples again because of this finite planar poset problem, where maybe there's some very difficult example that you can't draw reasonably, where you get different behaviour. I think I'll finish there.
Questions for me?
I think this goes like hand in hand with the Dushkin-Miller dimension. So is that chart up there with the examples, like the largest K such that G is a product of K non-trivial groups? Something like that.
Could be.
It looks like those examples.
Yeah, let's talk about it afterwards.
Any other questions or guesses?
So, you gave us this estimate relating dimensional coefficient systems to
Yeah.
posets. Do you know this is just an estimate? Are they always equal?
No, we don't know. We have a conjecture that if I give you Mackey functors for O, and then Mackey functors for O prime, where O prime has more transfers, more inductions than O, then the global dimension should decrease. It should be monotonic. But I don't think we managed to get that proven. So I think the answer is the best case we can do is the disk-like case. And then we have a conjecture that everything else is going to be lower global dimension than the corresponding maximal disk-like inside it. That's about as far as we've got.
Just a comment, the minus first K-theory group of the integral group ring of these groups has a similar pattern.
Okay.
So maybe we should talk about this afterwards.
Yeah,
I don't know if
please.
it's just a coincidence.
That's great. Anybody else? All right, well then we can get some coffee and let's thank Dave again.